What if instead of telling a computer exactly how to solve a problem step by step, you could just show it what the solution looks like and have it figure out the rules all by itself? That's a huge shift in thinking, right? Going from explicit rules to learned relationships. Well, that's the core idea of machine learning, and today we're going to unpack it.
Okay, let's make this real. Imagine you have to write a program to predict the price of a used car. Your first instinct might be to write a bunch of rules, right? Like, if the mileage is low, add some money. If it's a popular brand, add a bit more. But then you think about the age, the color, the condition, and pretty soon you are tangled in this massive web of if-then statements that could never ever account for every possibility. That whole approach is it's brittle, it doesn't scale. We've got to flip this problem on its head.
And that's really the heart of it. In traditional programming, you, the human, write every single explicit step-by-step rule. But with machine learning, you just provide the data, tons of it. You show it examples of cars and their prices, and the machine itself learns the rules. It finds all those subtle patterns and relationships that actually determine a car's value. It's a total flip from instruction to inference.
So, how are we going to tackle all this? Well, we've got a pretty clear path. First, we'll really nail down the difference between the old way and the new. Then, we'll get into the rules of the game for building a learning system. We'll meet the different styles of learning, watch out for some hidden dangers, and finally, uncover the universal truths that run the entire field.
All right, let's jump in with that paradigm shift. And I'm not kidding when I say that. This isn't just a new technique. It's a completely different way of thinking about how to solve problems.
So the old way, traditional programming, is kind of like writing a super detailed recipe. For our car problem, it would mean literally writing rules like, for every year older, subtract $1,000, and if the color is red, add 500. The key thing here is that a human programmer has to think of and code every single one of those rules. The logic is all out in the open. Machine learning just flips that on its head. Instead of writing the recipe, we build a chef. We give this chef thousands of examples of finished dishes, cars and their final prices, and its job is to taste them all and basically reverse engineer the recipe. It automatically discovers the patterns that lead to a good result.
Okay, so if we aren't writing the rules for the problem itself, what rules are we writing? Well, we still have to set up the game. So let's look at the 3 core things you need to design pretty much any machine learning system. It really boils down to 3 key steps. First, the model. This is like picking your tool. Are you trying to fit a simple, straight line to your data, or do you need something more flexible, more curvy? That initial assumption you make about the shape of the answer, that's called your inductive bias. Second, you need a loss function. Think of this as the scoreboard. It's just a formula that tells the model exactly how wrong its prediction was. Big number, big mistake. Small number, you're getting close. And third, optimization. This is the engine that tries to get the lowest score possible. It's an automated process that just tweaks the model's settings over and over, checks the scoreboard, and tries again, always hunting for the sweet spot that minimizes the error.
All right, so now we know how to set up the game. Let's meet the players. See, machine learning isn't just one thing. It's a whole field with different styles of learning, and each one is suited for a different kind of problem.
First up, and definitely the most common one you'll run into, is supervised learning.
The key word here is supervised, and for good reason. Think of it like learning with a teacher who gives you an answer key. You give the model a massive data set where every single example is already labeled with the correct output. Our used car problem? That's a perfect example. We give it thousands of car listings, and each one is labeled with its actual selling price. The model's whole job is to figure out the relationship between the car's features and that final price tag. This is a brilliant way to picture it. On the left, you have a bunch of shapes, and they're all labeled yes. On the right, a different set of shapes, all labeled no. The algorithm just studies these examples to figure out the rule. Is it the color? Is it the shape? By looking at enough labeled examples, it can then see a new shape and make a really good, educated guess. But what if you don't have an answer key? What if you just have a giant mountain of raw, unlabeled data? Well, that brings us to our next style, unsupervised learning. Here, the goal is pure discovery. You give the algorithm a ton of data without any labels and just ask it to find the hidden structure on its own. Imagine giving it all your customer purchase data. It might automatically discover distinct groups like the weekend bargain hunters, the high-value weekly shoppers, and maybe the one-time gift buyers. The magic here is that no human had to label anything beforehand. That makes it incredibly powerful for just exploring new data sets. Okay, our final style is a completely different beast. It's not about data points at all. It's about actions and consequences.
This is reinforcement learning. The best way to think about this is training an AI to play a video game. The AI player, that's the agent. The game world itself, that's the environment. The agent starts off just taking random actions, move left, jump, whatever. When it does something good, like grabbing a coin, we give it a positive reward. When it makes a mistake, like falling into a pit, it gets a penalty. Now, after millions of rounds of this trial and error, it doesn't just memorize moves. It learns a strategy, a policy for how to maximize its total score. This is the amazing idea behind AIs that can master insanely complex games like chess and Go. So, we have our learning system, we've picked a style. It seems pretty straightforward, right? But there are some classic traps we absolutely need to avoid. Let's talk about the hidden dangers. Here's the thing. The goal of machine learning is never just to be accurate on the data it has already seen. That's like a student who just memorizes the answers to a practice test but completely fails the real exam because they can't solve new problems. The real goal is to generalize, to perform well on new, unseen data. The training data is just the curriculum, the real world is the final exam. And this leads to something that might feel a little counterintuitive at first. You might think the best model is the one that perfectly, flawlessly fits every single training data point. But that's a trap. A simpler model that just captures the general trend, even if it ignores some of the noisy data points, is almost always going to be more useful in the real world. It's learned the signal, not the static. There's actually a formal name for this idea. It's a principle called Occam's razor. And all it really says is that when you're faced with a bunch of competing explanations, the simplest one is usually the right one. In machine learning, this means we want to shave off any unnecessary complexity from our model so it doesn't just end up memorizing the training data.
This all brings us to our final section, where we're going to look at two foundational theorems that are basically the laws of physics for machine learning. They really govern what's possible and what's not.
And this gets us to the fundamental tension in all of machine learning. It's called the bias-variance trade-off. So, a model that's too simple, one that makes really strong, rigid assumptions about the data, is said to have high bias. This is underfitting. It's just completely missing the underlying pattern. On the other end of the spectrum, a model that's way too complex, one that tries to fit every single data point perfectly, has high variance. This is overfitting. It's basically just memorizing the noise. The perfect model is somewhere in the middle. It's complex enough to capture the true pattern, but simple enough that it doesn't get distracted by the noise. Honestly, the entire craft of machine learning is just learning how to navigate this trade-off. And that leads to our final universal truth, something called the no free lunch theorem. And what it basically says is that there is no single master algorithm that is the best for every single problem. It's like a carpenter trying to build a house with only a hammer. It's not going to work. A data scientist can't solve every problem with the same model. That's why the field is so huge. We need a full toolbox with a different tool for every unique challenge the world throws at us. So there you have it. From rigid rules to flexible relationships, from designing a system to avoiding its biggest traps, you now understand the foundational ideas of machine learning. You've seen that core trade-off, and you know that there's no single magic bullet. You've got the map. The only question left is, where do you want to explore first?